Good afternoon, everyone. Our group and I are going to be presenting robotic face to simulate humans undergoing eye surgery. My name is Karina Zornoza.
My name is Ramos.
Valencia.
Shawnak, Verma.
First, we're going to show you a brief overview of what we're going to be going over today. Here's a quick agenda. So the primary objective for this project was to create a robotic face that had realistic eye and lid movement. The next primary objective was to create it as manufacturable and accessible as possible. Also, while creating it to be easily appended to other robotic applications. This is more so in the programming and software area. So the main motivation for creating this was because surgical procedures are very tedious and tiring. A doctor created a prototype slit lamp, seen in the picture on the right, that needs to be tested. So in order to test it before human trials, it needs to be tested in a different way. So that's why this robotic face to simulate that was created. Another reason was if we were to add more facial expressions to the face with robotic eye movement, it can be used in other applications such as for sign language teaching.
Before starting on with the project, our team did a comprehensive literature survey, and we found out that humanoids are basically the brainchild of Da Vinci. He made this armored knight, which you can see on your left. It could rotate its head and lift up its arms. More current prototypes which pertain to our project are Kismet, which is MIT's robotic face. It could mimic almost every human facial gesture.
For the programming surveys, the first thing we needed to do was to define what robotic programming was. And it's no more than a set of command or instructions to be able to move our hardware and to realize some autonomous tasks. Also, we needed to know the different type of programming that we could have done for the project. There is two different types that could have been applied to this project. One of them is online programming, and the other one is offline programming. For this prototype, we decided to go with the offline programming.
These are the related standards we used. Some of them are from a health and safety standpoint, and the others are from a robotic standpoint. Our project has a lot of global design implications. It's a training tool for ophthalmologists globally because once our design is up, anyone around the globe with a decent 3D printer can access our design and add the servo motors, and it's almost ready to go. And the manufacturing cost is inexpensive, and overall eye surgery is a global concern, and we're glad we're able to help them.
So these are the three different prototypes that we as a team came up with when we first started thinking about creating a face, a robotic face. So as you can see, the first prototype over here, the advantage of this prototype is that it's a compact design. It also uses PLA as a main frame. Uses a shaft tendon actuation system, and it actually requires assembly because it's composed of different parts. The second design is made of metal. It's also compact, but this one also requires assembly, and it uses a rigid shaft actuation system. And the last one is almost similar as the first one, but this one is we actually printed to see how the dimensions were fit in our face, because that was one of our boundaries. And so as you can see, it's a compact design, also made of plastic, but this one does not require assembly. So as you probably know, there's some challenges involved with the senior design. Some of them were for us with limited space and the precision on the tension and cable. So the way we solved this is basically we wanted to apply a little bit of the concepts that we use in industry, like Six Sigma, which is also it's highly used in manufacturability. So we use these two different concepts. And also, as you probably know, the team schedule is one of the biggest things when you're creating a senior project, because we are not only taking this class, but we're taking different classes, and some of us work already. So the way we solve this is we create a timesheet to account for all the different projects that we had for the phase, and also to account for the engineering hours that we're putting into this project. So this is our final design. We actually chose a combination of the first and the second design. So it's made of metal and PLA. So this is a CAP model, and this is the final configuration. We used 8 different servos for the motion of the face, and we have two different mechanisms to move the face. The first one is a RC control, and the second one is a program that we'll talk about later in the presentation. So these are two videos of testing the prototype. Over here, as you can see, we're trying to achieve accurate movement as a human would do. Same here, this is the full configuration, the eyelids closing and the eyes movement. So that's, we were testing the accuracy of the eyes. So we're not only mechanical engineers, we're material engineers as well. So we wanted to focus a little bit on the material that we use. And the reason we use PLA instead of other composites or like plastics is because it's a degradable material and is being used and nowadays more often. This is our cost analysis. So as you can see over here, we spent $434 on materials. And for the first prototype, as you know, the first prototype is always going to be the most expensive one for the rest. So here's a breakdown of all the different components, including the engineering hours. We calculated about 30 hours per hour, and that gave us a total of $1,474. But if we were to mass produce this prototype, we will not account for the design or programming time because we already have it. And also we got a quote for a better for a company to print our design, and we'll reduce it to 300 minutes. And that will give us a total of $754, which is 50% less than the first prototype.
So as I mentioned, one of our objectives was to make it easily manufacturable and accessible, meaning that the assembly also has to be simple. For our easily accessible parts, we included our CAD model. Our CAD parts can be 3D printed anywhere, including your home, and it can be customized or made into different proportions if you like as well. The items that we use, such as the steel thin wires, the servo motors, the tiny screws, the sizes are there, the glass eyes to make it look more realistic, and the mannequin face are also incredibly easy to access and cost effective as well. So the steps to construction are very simple as well. First, you start out by printing 3D parts, and after printing, you make sure that they're clean and free of any debris in order to make them easily assembled and put together. Next, you use your construction tools, whether it be pliers, power drills, or a screwdriver. The next part is to add the servo motors, which are what controls the movement in the eye, and then connecting those steel wires from the eyes to the servo and making sure that the tension is very accurate and precise. Next, we move on to the programming and software stage, which is adding the driver and connecting it to the Arduino, and then to the RC controller, which is what gives the person the power to control the movement of the eyes and the.
For the testing and evaluation section, we decided to split the work into 3 different sections. First one will be the motion analysis, our second one is SolidWorks simulation, and our last one is the software testing. For the first part of the engineering analysis, the motion analysis, our goal was to achieve a 14-degree opening from the center of the eye, meaning that using our 4-bar linkage mechanism displayed on the picture, our upper lid will open to about 14 degrees, and our lower eyelid will open to 104 degrees. This is measured from the center of the eye. Continuing engineering analysis, next thing we decided to go with is obtaining a factor of safety for our main frame. Our factor of safety came up to be 1.3, which means it's a safe prototype, although it might not be the safest prototype that we could have done, but this is due to the type of material that we decided to go with, which is plastic. On the right, on your right, you can see a 2D 4-bar linkage analysis, which was done in SolidWorks. This is just to better understand how the eyelids will move with respect to the servos. Then we move on to more SolidWorks simulations. On the left, we have a motion simulation, which is no more the eyeballs connected to the servos in order to better understand how the outside will be with respect to the servo. And on the right, you also see more stress analysis done on the main frame. we wanted to go more deep into the 4-bar linkages analysis because we wanted to make sure we were getting a realistic eyelid movement. So as you can see on the right, it's a 4-bar linkage example. On the left, with the help of our programming advisor, we created a MATLAB code that will predict where the end of the bar linkage will be with respect to the servo. At the end, after we were finished with our hardware, we needed to do the brain part. So we started testing our software. Since we were using servos, the first thing we wanted to know is the full range of the servos. This is why we decided to first calibrate the servos so we can see how much range we had to work with. Later on, we move on to using potentiometers. This is just to have a visual aid of how the eyeballs will move when we move the servos. Later on, as Steven said earlier in the presentation, we created an autonomous code which is no more than random movement for the eyeballs. All this was done using Arduino, which is an open source, so it's available for everyone. And later on, our final prototype is controlled thanks to RC control, and this one was also done using Arduino.
As you know, the senior design project is a group project, and it is all about teamwork. So this is the breakdown of responsibilities according to our team members' preferences and skills. In the future, we would really like to improve the software because every code can be optimized. On top of that, we would like to add more features like mouth and cheek so that the face looks more realistic. And the end goal is to incorporate some sign language teaching so that our robot can work in conjunction with the other robot. Next slide. So conclusively, the team was able to design, manufacture, and program a prototype which met our project objectives. We faced our fair share of setbacks and challenges, but we were able to resolve them within the stipulated time. And if we continue working in the future, as I said, by adding mouths and cheeks and other features, I think this could turn out to be we would really be able to improve this project. Apart from that, the team is really glad that it would be presenting this project in the 2017 Florida Conference for Recent Advancement in Robotics, which will be in May 11th. Last but not the least, very special thanks to Rodrigo Arredondo. He took a lot of time out of his already busy schedule to help us program our project, and also Melissa and Dr. Tosunoglu, who also helped us out. Thank you. Now we open the floor for questions.
How does your autonomous modeling work?
How does it work? It's just a random movement. So we give it a set of time, a range of time, to the Arduino. So let's say between 0 and 300 seconds, he will send PMWs, which is pulse per minute. They will send pulse to the driver, which will move the servo in a random direction.
So it's actually repeatable within the autonomous nature.
Pretty much it will repeat after a while, but it's not predictable. You can use the random. There's a random command on Arduino that you can use. So it will send a random number to the driver. The driver will read it and it will send it to the servo, and that's how we created the random movement.
To add, the doctor will test this with a laser machine. So he has to predict where the eyes will move to see if the laser is accurate enough to perform a surgery on humans. So basically, he will give the inputs for the programming or the coordinates for the eyes, so you can test if the laser machine is accurate enough for at least future testing.
Do you think about reflex?
Yeah.
What you could do for that?
We can probably add that in the future. That will be included into the sign language development that we want to do in the future, because this is suited for that application too. Since we have all the motions and we can add more to like the mouth and cheek, all the different motions for that.
I applaud you for keeping your time. You're the first team that's done that. And everybody, when they put a cost in, they put in a cost of what they wrote a check for, or paid cash at Home Depot, but there's a huge cost, much, much more than what you bought in pieces. As you found out by keeping your time, is the most expensive component of what you built.
Absolutely. If you were gonna send this to a machine shop, they would charge you not only for the parts, but for the engineering time that they will put into machines, and also the running time for that. So we wanted to make it as realistic as possible, and that the price, the final price as mass produced, is actually very realistic to what we need to what we actually need.
How did you come up with that price? Was it, you made certain assumptions, or did you actually quote this project?
We bought everything. So all the pieces, the material, we bought everything. So with that price, we already have. And the engineering time, the $38 per hour, we actually got that price from our manufacturing class. With like if you have a spreadsheet that's something similar to this one, and the professor told us that it ranges between like $30. So we actually went with that. The averages.
So it's an estimate.
It's an estimate. Yeah, it's an estimate. Yeah.
But you kept your actual time. You turned in little time slips every time you worked on the project?
Absolutely, yeah. So
Right.
the project was left in the robotics lab. So whenever one of those will go there and work on the prototype, we'll record the time that you spent on whatever you were doing in the lab.
You might be paying somebody $20 an hour to do this job, but in reality, a shop labor rate in my technical business is something over $100 an hour. And that includes all the machinery, equipment, overhead, that kind of thing.
Well, this is printed in with a 3D printer. So basically, you input the STL file and they just later run.
Right.
So I guess that will take care of the machining time. There's actually no machining on this prototype, but maybe we can include that in the future.
Yeah, well, that's kind of automatic time when it's doing that. I'm assuming you didn't turn the time slip in for the 3 hours and 47 seconds it took to print it. I would assume that you turned your time slip in for the time it took you to program the 3D printer,
Yes.
load the plastic in, load the part in.
Absolutely, yes, sir.
It's for all of that. That's good. It's the right way to do it.
Any more questions?
What were the Six Sigma principles that you used on your project?
Let me go back to it. So we went to, actually we didn't use Six Sigma, the one we used was ACE, which is used by I work for UTC, so we use that for manufacturing, for the lean lines and all that stuff. So we wanted to use something similar, so since ACE is not well known, we wanted to use Six Sigma, which is similar to it, but it's basically the same concept. If you want to improve a concept, you get together with your group, you brainstorm ideas, then you plan for it, and then you divide the tasks, and you see how you can solve it. So that's how we did.
So what ACE principles did you use?
We use well, I can recall the names, but that's basically the process. That's called I don't have the name right now, but that's basically that's the way you go with it. You get together with your group, you brainstorm, you divide the task, and then each one gets that done, and then you put everything together. That's how we solved the tension problem, because we were using a fishing line first, and we saw that was not very effective because of the tension. So we changed and we brainstormed, and then that's how we in the end we use cable for that.
It's root cause corrective action. That's a type.
Correct. Yes. I mean, I don't have the name on top of my head, but I'm pretty sure I'll do it in the future.
Thank you.
No problem.